Hello everyone, this is Srijit. Welcome to MCAC 35 Advanced Database Management Systems. Today we will discuss information retrieval. The term information retrieval generally refers to the querying of unstructured textual data. Information retrieval systems have much in common with database systems, in particular the storage and retrieval of data on secondary storage. However, the emphasis in the field of information systems is different from that in database systems, concentrating on issues such as querying based on keywords, the relevance of documents to the query, and analysis, classification, and indexing of documents. Today we will cover these topics: relevance ranking using terms, relevance using hyperlinks, synonyms, homonyms, and ontologies, indexing of documents, measuring retrieval effectiveness, web search engines, and information retrieval and structured data. The field of information retrieval has developed in parallel with the field of databases. In the traditional model used in the field of information retrieval, information is organized into documents, and it is assumed that there is a large number of documents. Data contained in documents are unstructured without any associated schema. The process of information retrieval consists of locating relevant documents on the basis of user inputs such as keywords or example documents. For example, find documents containing the word database systems can be used even on textual descriptions provided with the non-textual data such as images. Web search engines are the most familiar example of information retrieval systems. Other traditional examples of information retrieval systems are online library catalogs and online document management systems such as those that store newspaper articles. The data in such systems are organized as a collection of documents. A newspaper article and a catalog entry in a library catalog are examples of such documents. Now let's see the difference between database systems and an information retrieval system. Database systems deal with several operations that are not addressed in information retrieval system. For instance, database systems deal with updates and with associated transactional requirements of concurrency control and durability. These matters are viewed as less important in information systems. Similarly, database systems deal with structured information organized with relatively complex data models, such as the relational model or object-oriented data models. Whereas information retrieval systems traditionally have used a much simpler model where the information in the database is organized simply as a collection of unstructured documents. Information retrieval systems deal with several issues that have not been addressed adequately in database systems. For instance, the field of information retrieval has dealt with the issue of querying collections of unstructured documents, focusing on issues such as keyword queries and of tracking of documents on estimated degree of relevance of the documents to the query. Now let's see what is keyword search. In addition to simple keyword queries that are just sets of words, information retrieval systems typically allow query expressions formed using keywords and the logical connectives and, or, and not. For example, a user could ask for all documents that contain the keywords motorcycle and maintenance, or documents that contain the keywords computer or microprocessor, or even documents that contain the keyword computer but no database. A query containing keywords without any of the above connectives is assumed to have ands implicitly connecting the keywords. Ranking of documents on the basis of estimated relevance to a query is critical. Relevance ranking is based on the factors such as term frequency, that is the frequency of occurrence of query keyword in document, inverse document frequency, which is how many documents the query keyword occurs in. Fewer the occurrence gives more importance to the keyword, and hyperlinks to documents. More links to a document means that document is more important. Information retrieval systems, as exemplified by web search engines, have today evolved beyond just retrieving document based on a ranking scheme. Today, search engines aim to satisfy a user's information needs by judging what topic a query is about and displaying not only web pages judged as relevant but also displaying other kinds of information about the topic. For example, given a query termed cricket, a search engine may display scores from ongoing or recent cricket matches rather than just display top ranked documents related to cricket. Now let's see relevance ranking using terms. The set of all documents that satisfy a query expression may be very large. Information retrieval systems therefore estimate the relevance of documents to a query and return only highly ranked documents and answers. Ranking using term frequency inverse document frequency or TF-IDF. In full text retrieval, all the words in each document are considered to be keywords. For unstructured documents, full text retrieval is essential since there may be no information about what words in the document are keywords. We shall use the word term to refer to the words in a document since all words are keywords. Given a particular term T, how relevant is a particular document D to the term? One approach is to use the number of occurrences of the term in the document as a measure of the relevance, called term frequency or TF. One way of measuring term frequency of a particular term T on a document D, the relevance of document D to a term T is given as a log of 1 plus NDT divided by ND, where N of D denotes the number of terms in the document and NDT denotes the number of occurrence of the term T in the document D. A query Q may contain multiple keywords. The relevance of a document to a query with the two or more keywords is estimated by combining the relevance measures of the document to each keyword. A simple way of combining the measures is to add them up. But there is an issue. Suppose a query uses two terms, one of which occurs frequently, such as database, and another that less frequent, such as pod. A document containing pod but not database should be ranked higher than a document containing the term database but not pod. To fix the above problem, weights are assigned to terms using the inverse document frequency defined as IDF of T is equal to 1 by N of T. Thus, the relevance of a document D to a set of terms Q is then defined as RDQ is equal to sum over every term belongs to the set Q TF of DT into IDF of T, or term frequency of the term T on a document D into inverse document frequency of the term summed to all T that belongs to the particular set Q. This measure can be further refined if the user is permitted to specify weights W of T for terms in the query, in which case the user specified weights are also taken into account by multiplying T of T by W of T in the above formula. The above approach of using term frequency and inverse document frequency as a measure of the relevance of a document is called the TF-IDF approach. Almost all text documents in English contain words such as and, or, a, and so on, and hence these words are useless for querying purposes since their inverse document frequency is extremely low. Information retrieval system define a set of words called stop words containing 100 or so of the most common words and ignore these words when indexing a document. Such words are not used as keywords and are discarded if present in the keywords supplied by the user. Another factor taken into account when a query containing multiple terms is the proximity of the terms in the document. If the terms occur close to each other in the document would be ranked higher than if they occur far apart. The formula for RDQ can be modified to take proximity of the terms into account. Given a query Q, the job of an information retrieval system is to return documents in the descending order of their relevance to Q. Since there may be a very large number of documents that are relevant, information retrieval systems typically return only the first few documents with the highest degree of estimated relevance and permit users to interactively request further documents. Now let's see similarity-based retrieval. Certain information retrieval systems permit similarity-based retrieval. Here, the user can give the system document A and ask the system to retrieve documents that are similar to A. The similarity of a document to another may be defined, for example, on the basis of common terms. One approach is to find k terms in A with highest values of TF-AT into IDF-T and to use these k terms as a query to find the relevance of other documents. The terms in the query are themselves weighed by TF-AT into IDF-T, or time frequency of particular T on a document A into inverse document frequency of the term T. Relevance feedback. If the set of documents similar to a query document A is large, the system may present the user a few of the similar documents, allow the user to choose the most relevant few, and start a new search based on similarity to A and to the chosen documents. The resultant set of documents is likely to be what the user intended to find. This idea is called relevance feedback. Duplicates should be detected and only one copy should be returned as the answer. Then what is vector space model? Let there be n words overall across the documents being considered, and an n-dimensional space is defined with each word as one of the dimensions. A document D is represented by a point in this space with the value of the ith coordinate of the point being r, d, ti. The vector for document D connects the origin, all coordinates is equal to 0, to the point representing the document. The model of documents as points and vectors in an n-dimensional space is called the vector space model. The cosine of the angle between the vectors of two documents is used as the measure of their similarity. That simply means we will define a vector plane, we will mark the documents as points, and we will draw lines from the origin to the point, and we will measure the angles between these lines. The cosine of these angles shows the similarity of these documents, or measure of similarity. Next, let's see relevance using hyperlinks. Early web search engines ranked documents by using only TF-IDF based relevance measures. These techniques had some limitations when used on very large collections of documents, such as a set of all web pages. In particular, many web pages have all the keywords specified in a typical search engine query. Further, some of the pages that users want as answers often have just a few occurrences of the query terms and would not get a very high TF-IDF score. Search engine spamming refers to the practice of creating web pages or sets of web pages designed to get a high relevance rank for some queries, even though the sites are not actually popular sites. For example, a travel site may want to be ranked high for queries with the keywords travel. It can get high TF-IDF scores by repeating the word travel many times in its page. Even a site unrelated to travel, such as a pornographic site, could do the same thing and would get highly ranked for a query on the word travel. In fact, this sort of spamming of TF-IDF was common in the early days of the web search, and there was a constant battle between such sites and search engines that tried to detect spamming and deny them in high ranking. Popularity ranking. The basic idea of popularity ranking, also called prestige ranking, is to find pages that are popular and to rank them higher than other pages that contain specified keywords. Since most searches are intended to find information from popular pages, ranking such pages higher is generally a good idea. For instance, the term Google may occur in vast numbers of pages, but the page google.com is the most popular among the pages that contain the term Google. The page google.com should therefore be ranked as the most relevant answer to a query consisting of the term Google. TF-IDF can be combined with popularity to get an overall relevance value. Now the problem arises is how to find the popularity. The first solution to estimating the popularity of a page is to use the number of pages that link to a page as a measure of its popularity. However, this by itself has the drawback that many sites have a number of useful pages, yet external links often point only to the root page of that site. The root page in turn has links to the other pages in the site. These other pages would then be wrongly inferred to be not very popular and would have a low ranking in answering queries. One alternative is to associate popularity with sites rather than with pages. All pages at a site that get the popularity of the site and pages other than the root page of popular site would also benefit from the site's popularity. However, there are many sites that host a large number of mostly unrelated pages such as homepage servers in universities and web portals. For such sites, the popularity of one part of the site does not imply popularity of another part of the site. A simpler alternative is to allow transfer of prestige from popular pages to which they link. Under this scheme, in contrast to the one person, one vote principle of democracy, a link from a popular page X to a page Y is treated as conferring more prestige to page Y than a link from a not so popular page Z. This notion of popularity is in fact circular, since the popularity of a page is defined by the popularity of other pages and there may be cycles of links between pages. However, the popularity of pages can be defined by a system of simultaneous linear equations which can be solved by matrix manipulation techniques. The linear equations can be defined in such a way that they have a unique and well-defined solution. The page rank. The web search engine Google introduced page rank, which is a measure of popularity of a page based on the popularity of pages that link to the page. Using the page rank popularity measure to rank answers to a query gave results so much better than previously used ranking techniques that Google became the most widely used search engine in a rather short period of time. Now let's see the connection to social networking theories that rank prestige of people. For example, the president of USA has a high prestige since many people know him. So someone known by multiple prestigious people has high prestige. Hub and authority-based ranking. A hub is a page that shows links to many pages on a topic, and an authority is a page that contains actual information on the topic. Each page gets a hub prestige based on prestige of authorities that it points to, and each page gets an authority prestige based on the prestige of hubs that points to it. Again, prestige definitions are cyclic and can be got by solving linear equations. So use authority prestige when ranking answers to a query. Now let's see synonyms and homonyms. Consider the problem of locating documents about motorcycle maintenance using the query motorcycle maintenance. Suppose that the keywords of each document are the words in the title and the names of the authors. The document titled motorcycle repair would not be retrieved since the word maintenance does not occur in this title. We can solve that problem by making use of synonyms. Each word can have a set of synonyms defined, and the occurrence of a word can be replaced by the or of all its synonyms, including the word itself. Thus, the query motorcycle and repair can be replaced by motorcycle and repair or maintenance. This query would find the desired document. Keyword-based queries also suffer from the opposite problem of homonyms, that is, single word with multiple meaning. For instance, the word object has different meanings as a noun and as a verb. The word table may refer to a dinner table or to a table in a relational database. There is a danger even with using synonyms to extend queries is that the synonyms may themselves have different meanings. For example, allowance is a synonym for the meaning of the word maintenance but has a different meaning than what the user intended in the query motorcycle maintenance. Documents that use the synonyms with an alternative intended meaning would be retrieved. It is therefore a bad idea to use synonyms to extend a query without first verifying synonyms with the user. Next, let's see concept-based querying. A better approach to the above problem is for the system to understand what concept each word in a document represents, and similarly to understand what concept a user is looking for, and to return documents that addresses the concept that the user is interested in. A system that supports concept-based querying has to analyze each document to disambiguate each word in the document and replace it with the concept of that it represents. Concept-based querying has several advantages. For example, a query on one language can retrieve documents on other languages so long as they relate to the same concept. Ontologies are hierarchical structures that reflect the relationship between concepts. The most common relationship is the easy relationship. For example, a leopard is a mammal and a mammal is an animal. Other relationships such as part of are also possible. For example, an aeroplane wing is part of an aeroplane. In addition to language-wide ontologies, ontologies have been defined for specific areas to deal with terminology relevant to those areas. For example, ontologies have been created to standardize terms used in businesses. That is an important step in building standard infrastructure for handling order processing and other inter-organization flow of data. It is also possible to build ontologies that link multiple languages. The largest effort in using ontologies for concept-based queries is the semantic web. The semantic web is led by the World Wide Web Consortium and consists of a collection of tools, standards, and languages that permit data on the web to be connected based on the semantics or meaning. Now let's see indexing of documents. An effective index structure is important for efficient processing of queries in an information retrieval system. Documents that contain a specified keyword can be located efficiently by using an inverted index that maps each keyword ki to a list of si of the documents that contains ki. For example, if documents D1, D9 and D21 contain the terms ADBMS, the inverted list for the keyword ADBMS would be D1, D9, D21. To support the relevance ranking based on proximity of keywords such as index may provide not just identifiers of the documents but also a list of locations within the documents where the keyword appears. For example, if ADBMS appears in positions 21 in D1, positions 1 and 19 in D2 and positions 4, 29 and 46 in D3, the inverted list with the positions would be D1 bar 21, D9 bar 1, 19, D21 bar 4, 29, 46. The inverted list may also include with each document the term frequency of the term. The AND operation finds documents that contain all of the specified set of keywords K1, K2 to Kn. We implement the AND operation by first retrieving the sets of document identifiers S1, S2, etc. to Sn of all documents that contain the respective keywords. The intersections S1 intersection S2 intersection etc to xn of the sets give the document identifiers of the desired set of documents. The OR operations gives the set of all documents that contain at least one of the keywords K1, K2 to Kn. We implement the OR operation by computing the union S1 union S2 union etc to Sn of the sets. The NOT operation finds documents that do not contain a specified keyword Ki. Given a set of document identifiers S, we can eliminate documents that contain the specified keyword Ki by taking the difference S difference Si, where Si is the set of identifiers of documents that contain the specific keyword Ki. Given a set of keywords in a query, many information retrieval systems do not insist that the retrieved document contain all the keywords unless an AND operation is used explicitly. In this case, all documents containing at least one of the words are retrieved, as in the OR operation, but are taken by their relevance measure. To use term frequency for ranking, the index structure should additionally maintain the number of times terms occur in each document. To reduce this effort, they may use a compressed representation with only a few bits that approximates the term frequency. Measuring retrieval effectiveness. Each keyword may be contained in a large number of documents. Hence, a compact representation is critical to keep space usage of the index low. Thus, the sets of documents for a keyword are maintained in a compressed form so that storage space is saved. The index is sometimes stored such that the retrieval is approximate. A few relevant documents may not be retrieved, called a false drop or false negative, or a few irrelevant documents may be retrieved, called a false positive. A good index structure will not have any false drops, but may permit a few false positives. The system can filter them away later by looking at the keywords that they actually contain. In web indexing, false positives are not desirable either, since the actual document may not be quickly accessible for filtering. Two matrices are used to measure how well an information retrieval system is able to answer queries. The first is precision. That's the measures what percentage of the retrieved document are actually relevant to the query. The second, recall, measures what percentage of the document relevant to the query were retrieved. Ideally, both should be 100%. Precision and recall are also important measures for understanding how well a particular document ranking strategy performs. Ranking strategies can result in false negatives and false positives, but in a more suitable sense. False negatives may occur when documents are ranked as a result of relevant documents receiving a low ranking. If the system fetches all documents down to those with a very low ranking, there would be very few false negatives. Therefore, instead of having a single number as a measure of recall, we can measure the recall as a function of the number of documents fetched. False positive may occur because irrelevant documents get higher ranking than relevant documents. This too depends on how many documents are examined. One option is to measure precision as a function of number of documents fetched. A better and more intuitive alternative for measuring precision is to measure it as a function of recall. With this combined measure, both precision and recall can be computed as a function of number of documents if required. For instance, we can say that with a recall of 50%, the precision was 75%, whereas at a recall of 75%, the precision dropped to 60%. In general, we can draw a graph relating precision to recall. These measures can be computed for individual queries, then averaged out across a suite of queries in a query benchmark. Another problem with measuring precision and recall lies in how to define which documents are really relevant and which are not. In fact, it requires understanding of natural language and understanding of the intent of the query to decide if a document is relevant or not. Researchers therefore have created collections of documents and queries and have manually tagged documents as relevant or irrelevant to the queries. Different ranking systems can be run on these collections to measure their average precision and recall across multiple queries. Now let's see crawling and indexing the web. Web crawlers are programs that locate and gather information on the web. They recursively follow hyperlinks present in known documents to find other documents. Crawlers start from an initial set of URLs which may be created manually. Each of the pages identified by these URLs are fetched from the web. The web crawler then locates all URL links in these pages and adds them to the set of URLs to be crawled if they have not already been fetched or added to the to be crawled list. This process is again repeated by fetching all pages on to be crawled set and processing the links in these pages in the same fashion. By repeating the process, all pages that are reachable by any sequence of links from the initial set of URLs would be eventually fetched. Since the number of documents on the web is very large, it is not possible to crawl the whole web in a short period of time, and in fact, all search engines cover only some portions of the web, not all of it. And their crawlers may take weeks or months to perform a single crawl of all the pages they cover. There are usually many processes running on multiple machines involved in crawling. A database stores a set of links or sites to be crawled. It assigns links from these sets to each crawler process. New links found during a crawl are added to the database and may be crawled later if they are not crawled immediately. Pages have to be refetched, that is, links recrawled periodically to obtain updated information and to discard sites that no longer exist, so that the information in the search index is kept reasonably up to date. Pages fetched during a crawl are handed over to a Prestige computation and indexing system which may be running on a different machine. The Prestige computation and indexing system themselves run on multiple machines in parallel. Pages can be discarded after they are used for Prestige calculation and added to inbox. However, they are usually cached by the search engine to give search engine users fast access to the cached copy of a page, even if the original website containing the page is not accessible. It is not a good idea to add pages to the same index that is being used for queries, since doing so would require concurrency control on the index and would affect query and update performance. Instead, one copy of the index is used to answer queries while another copy is updated with newly crawled pages. At periodic intervals, the copies switch over, with the old one being updated while the new copy is being used for queries. To support very high query rates, the indices may be kept in main memory, and there are multiple machines. The system selectively routes queries to the machines to balance the load among them. Popular search engines often have tens and thousands of machines carrying out the various types of crawling, indexing, and answering user queries. There are something called deep web crawlers. Those things extract some such information by guessing what terms would make sense to enter or what menu options to choose in such search interfaces. By entering each possible term or option that executing the search interface, they are able to extract pages with data that would not be been able to find otherwise. The pages extracted by the deep web crawlers may be indexed just like regular web pages. The Google search engine, for example, includes results from deep web crawls. Information retrieval and structured data. Information retrieval system originally treated documents as a collection of words, and information extraction systems infer structure from these documents. For example, extraction of house attributes such as size, address, number of bedrooms, etc. from a text advertisement, or extraction of a topic and pupil names from a new article. Search engines designed for finding scholarly research articles such as CiteSeer or Google Scholar crawl the web to retrieve documents that are likely to be research articles. They examine some features of each retrieved document, such as the presence of words such as bibliography, references, and abstract, to judge if a document is in fact a scholarly research article. They then extract the title, list of authors, and the citations at the end of the article by using information extraction techniques. The extraction citation information can be used to link each article to articles that it cites or to articles that cite it. Such citation links between articles can be very useful for a researcher. Now let's see querying on structured data. Structured data are primarily represented in either relational or XML form. Several systems have been built to support keyword querying on relational and XML data. So relations or XML structures used to store this extracted data, and system seeks connection among data to answer queries. Okay, then we have question answering systems. Question answering systems attempts to provide direct answers to questions posed by users. Question answering systems targeted at information on the web typically generate one or more keyword queries from a submitted question, execute the keyword queries against web search engines, and pass return documents to find segments of the documents that answer the question. A number of linguistic techniques and heuristics are used to generate keyword queries and to find relevant segments from the document. So this marks the end of the topic, information retrieval system and the module. So let's see with a new topic and a new module in the next class. Thank you for listening.